Okay, let's continue with our discussion on mesh current analysis. So mesh current analysis, similar to node voltage analysis, we apply a certain technique to obtain equations, and then we solve for the unknown variables. In case of node voltage, we applied KCL, and we use KCL to to write down our equations. In case of mesh current analysis, we use KVL to write down voltage equations and then solve for the unknown variables. So just a brief recap, the first step was to identify the meshes and assign mesh currents and choose a direction for those mesh currents. And once we have the directions, we know that they would cause a voltage drop in the resistors. Those voltage drops can be defined in terms of the mesh current variables, and then we solve for those mesh current values. In this example, we have three meshes, three mesh currents, I1, I2, and I3. And the first mesh, this is the bottom left, I named it as M1. M1 has two resistors, R2 and R3, and both of them are shared branches. Shared branches as in they are shared between mesh 1, 2, and 3. So when that happens, you have two mesh currents flowing through the same resistor, which of course does not have a physical basis. It's not real. Mesh currents are hypothetical. They are not real. And so if you have two mesh currents flowing in the same resistor, you have to account for both voltage drops. And so we wrote down the first equation for mesh 1, and I'm applying KVL in a counterclockwise direction. So I have minus VA minus VR2, minus VA plus VR2 minus VR2 plus VR3 and minus VR3. Now, the reason we have it minus is because of the chosen direction of the current. For I2 and I3, both of them are going in the opposite direction of the KVL, okay? Important to note, it does not matter what direction you choose for your mesh currents, and it is not important in which direction you add up the voltages. Okay, I could add up the voltages in a counterclockwise direction, and I would still end up with the exact same equation. No difference. I could add up KVL in this direction. Then my equation would be, so this is clockwise direction. And this would be counterclockwise. So if I add up in this way, first voltage I encounter is VR3. I would write minus VR3, and this would be due to I1. And then plus VR3 due to I2. And then minus VR2 due to I1 and plus VR2 due to I3 plus VA equals 0. Take a look at every component and you will see that it is the exact same equation. Does that make sense? So again, it does not matter which direction you choose for your mesh currents. It also does not matter which direction you add up the KVL voltages. As long as you're consistent within that problem, within that analysis, your answers will always end up being correct. It's two different things. Again, KVL summing voltages, you're going around a loop. So you add up the voltages around a loop. So you pick a direction for adding the voltages, and then the mesh current directions also are arbitrary. I could choose the mesh currents to all go in the same direction. Something like this. If I have I1 going in this direction, I could choose I2 going in the opposite direction, which would cause the voltage drops to be in the same direction for that branch. So if I did this, and this is I2, now my voltage drops through both resistors are in the exact same direction. So instead of it being I1 minus I2 or I2 minus I3, it would simply be a plus. You would still end up with the right answer at the end of your analysis. Okay. So again, similar to node voltage analysis, it does not matter what current direction you choose. So in mesh current analysis, it's the exact same thing. It does not matter which direction you choose for your mesh currents. You will always end up with the right answer. The only thing is, once you choose a direction for your mesh currents at the beginning of your analysis, you cannot change it halfway through your solution. You have to stick with the same direction till the end. All right, any questions? Does that make sense? See some nods. Monday morning blues. All right, mesh 2. I'm going to move this. Actually, just leave. And is arbitrary. It does not matter in the sense it's not correct. And the reason is when you go to mesh 2 and mesh 3, you're going to use the exact same current direction. So the equations that you would have for those meshes would counteract these. Okay. They will work in conjunction with these, and you will end up with the right answer. So let's go to mesh 2. In mesh 2, I have 2 resistors and a voltage source. VB, R3, and R4. R3, R4. And I have a clockwise direction for my mesh current. I2. And of course, I1. So now mesh 2, I2 is the dominant current. And so I'm going to assign a polarity based off of current I2. I have plus and minus. Again, remember, point of entry is plus, point of exit is minus. And so in this case, if I apply KVL, again, the clockwise direction, starting at the bottom left corner, I have VR3 due to I2 minus VR3 due to I1 plus VB plus VR4 due to I2 minus VR4. Actually, no, that is not shared. It is simply equal to 0. So VR4 is not a shared branch.
Professor, would you need two VBs for the I3?
No, because it's a voltage source. So we cannot describe a voltage source using the current I3.
Why is there a negative VP though? Because it's like the current is like there's current going through it in the opposite direction.
No, the current is, so it does not matter. We are applying KVL. And when we apply KVL, we are simply adding up the voltages. So here VB is already given to us like this, right? I'm simply adding up my voltages in this direction. And my technique of applying KVL is if I encounter a voltage and the plus sign first, then I add the voltage. If it's a minus sign first, then I subtract the voltage.
So the current I3 going through that branch doesn't have an effect on that loop.
So it doesn't have, so not on the voltage source. No. So again, remember, we assume mesh currents so that we can describe the resistor voltages, but it does not affect the current source or a voltage source. We simply just add the voltage source as they are. So the question being asked was about mesh currents affecting the source, and the answer it doesn't. Mesh currents only allow us or permit us to describe the resistor voltages. And that's the only purpose actually. So again, going back to node voltage analysis, we assume branch currents. The reason we assume branch currents is because we want to describe the component resistor voltages in terms of the node voltages. So we apply KCL. In mesh current analysis, we are choosing mesh currents. Again, remember, they are not real, but the only purpose of choosing mesh currents is so that we can describe the resistor voltages that are present in that loop. So we can sum up those voltages. If we have a voltage source, and it's automatic, we simply add the voltage or subtract the voltage, as the case may be. But it does not affect, the mesh current itself does not affect the voltage source. If there is a current source in there, and we look at the example which has a current source, it makes it easier. It's like a voltage source connected for node voltage analysis. It automatically gives us an answer or a value for one of the unknown mesh currents. And let's see this example. Yeah, it just has a resistor and voltage source. Okay, any other questions regarding the equation or the technique so far? Yes.
To clarify that point, so just normally, if the current is going, so we're using other techniques, if the current is going in the same direction as the voltage source is going, so entering
For KVL direction or for the mesh currents?
So that would be for KVL, and for mesh current, it would enter positive, not.
No. So, and this is a very common thing. It's because, you know, unlike node voltage, there we are dealing with like two directions here. KVL direction actually does not, well, neither direction actually matters. But KVL direction is simply the direction I choose to add up the voltages, right? And as I said, students can have their own technique on how they're adding up voltages. So I always say, you know, I'm going to take a direction for summing up the voltages. So don't get, I would say, do not get confused with the mesh currents and the KVL direction. The mesh current is simply, it's assumed so that we can simply describe the voltage across a resistor. And that's it. It does not affect voltage source VB. So even if voltage source VB had like a minus or a plus, like this, the mesh current has no effect whatsoever. It does not affect it at all. We do not even care about it when it comes to a voltage source or even a current source for that matter. We simply want to apply KVL and add up the voltages around a loop. And to add up the voltages, we need to add up the voltages or to sum up the voltages. To sum up the voltages around this loop, we need to describe the voltage across R4 and the voltage across R3. And to describe those voltages, we assume a hypothetical current that is flowing through that mesh. Does that make sense?
Thank you.
Yes.
So in these equations are, so V R3 due to I2, is I2 another variable? Or is that?
No, I2 is the mesh current.
I'm just saying in our expression, in our equation.
Oh,
is that
here?
something to solve for, is that a subscript?
That's just a subscript. We are solving for I2, but this is just a subscript for now. So VR3 due to I2 would actually become, or if I was going to write it directly, I would just simply say here, because it's a shared branch. This is not shared. R4 is not shared. So I would simply write VR3 would be equal to I2 minus I1 times R3. This is how I would write it directly. I do this step to explain to students how we arrive at this quantity. This is just a subscript. I'm saying VR3 due to I2 and then VR3 due to I1. That's it. It's only for my classes, basically, if you want to call it that. Does that make sense? It's just a subscript and a notation, nothing else.
Right, so then what are we solving? Actually, yeah, maybe I'll let you get to.
We will write the expression. So our node voltage analysis, we first write the KCL expression, then we apply Ohm's law. So we haven't gotten to that step yet. And then mesh 3. Actually, since we're talking about that, let's go ahead and do that. Before I do mesh 3, let's just apply Ohm's law and then express each resistor voltage in terms of the mesh current. So let's do that right now. So if I apply Ohm's law and express each voltage in terms of the current, I would get R3 times I2 minus I1 plus VB plus I2 times R4 equals 0. So this, again, it's I2 minus I1 just because my current direction is opposite. Okay, these two currents, I1 and I2 are flowing in the opposite directions. If they were flowing in the same direction, I would have I1 plus I2. Or if they were both the opposite of the KVL direction, I would have minus I1 minus I2. But again, that depends on the direction of your mesh current, your assumptions, and then how you add up your voltages around KVL. There's not enough time in a class, otherwise I would show all approaches. just to show that it does not actually matter which direction you choose your KVL and which direction you choose for your mesh current. And here, if I write an expression here, I would have I2 minus I1. Actually, let's stick with the first one. Minus VA plus I1 minus I3 times R2 plus I1 minus I2 times R3 is equal to 0. So if you want to understand this better, I would suggest you choose a opposite current direction and write a KVL and see if you arrive at those exact same equations. Shouldn't take you longer than 5 or 10 minutes. And then mesh 3. R1, R2, and VB, and I3. R1, R2, and VB. And in this case, now from KVL clockwise, I'm going to have I1 flowing in this direction, and then plus minus. So I would have VR1 minus VB plus VR2 due to I3 and minus VR2 due to I1 equals 0. See, if you read about these instructions in a book, they will not do this step. Okay, they will not show you this step where you have two different voltages for the same resistor. It would simply be I1 minus I2 or I2 minus I1. From Ohm's law, I can write VR1 is the voltage drop due to I3 minus VB and plus I3 minus I1 times R2 is equal to 0. At this point, you would plug in all known values into these equations. And then you would solve for the unknowns. Again, once you plug in the values, it's the same system set of algebraic equations. You solve it using any technique you want, and then you find the values for the mesh currents I1, I2, and I3, which we will do next class. So we'll end class here today. If you have any questions, I'm around. Also, we have office hours later this afternoon. Look over the homework, mesh current analysis. Again, introduce the topic on Friday. Perhaps you might not have had time yet, but strongly recommend you open it up today and get working on this. And then one other thing, which I just mentioned earlier, was you assume a different direction for your mesh currents, and then you derive those three equations and see if they match up with these three. All right. Have a good day, and I will see you all on Monday. Wednesday.
And you have to talk about-